So our first talk is by Jim Dye. He's the Leon C. Welch Professor of Engineering at Cornell. He's got a long-standing and significant contributions to the queuing community. He has won the Erlang Prize, given the Markov Lecture, was the editor-in-chief of Mathematics of Operations Research. His interests are in resource allocation, semiconductor wafer fabrication, computer and communication systems, behavior and service systems, and hospitals and ride sharing. Also methodologically, we know Jim for many of us have used Jim's work in fluid limits and their consequences on positive recurrence as well. More recently, he's been working on reinforcement learning in queuing systems, and as I've mentioned previously, he's been very good at articulating the challenges in that research area, but also coming about and looking at practical solutions for applying reinforcement learning in queuing systems. So I'll take it away for Jim. Thank you very much.
Good. All right. Thank you, Neil, for the introduction, and I also thank for the organizers, particularly Peter Taylor, for the invitation to speak at this workshop. It's very nice. I attended some of the yesterday's sessions. Very much enjoyed. So it's also good. I cannot see you, the audience, but it's I hope that this pandemic will be over very sooner than so that we can meet in person, interact in person. We really need that. So today I'm going to talk about this recent work in the last few years with my collaborator. So the deep reinforced learning for stochastic processing networks. My collaborator is a current PhD student at Cornell University, and actually he's graduating. And he's from the Applied Center for Applied Mathematics. So I'm not going to tell a big story here, but it's very clear that you heard of these things, AlphaGo Zero, etc. So deep reinforced learning is the core methodology driven these successes. And I will particularly mention this robotics. Okay, so now Amazon warehouse start to deploy robotics. So as I understand it, for robust control, reinforced learning, deep reinforced learning is a major pathway leading robotic control. So the question here, a lot of us here in this audience, and myself included, we are interested in operations, improving operations. And I'm in a department called Operation Research. It's prominently there, the name. So the example of operations that are important are data centers, hospital operations, ride-hailing platform like Uber, Lyft, and supply chain logistics. I mean, like Amazon's fulfillment system, etc. So these systems are very different from game like AlphaGo Zero or for robotics, right? First of all, these systems operate different time scale different. We understand time scale is tremendously important, and also because it's time scale, the demand or customer behavior changes over time, and these issues actually was very much discussed in Peter Glenn's talk yesterday, very well articulated, and these challenges there. So the question here is that, so I think the first bullet point here is that deep reinforced learning is yet to prove let me just close this here, okay. Yet to prove its efficacy or the usefulness for operational problems. Okay, so this is something that is yet to prove its success. By operational problem, I'm thinking of data centers operations, right? Ride-hailing platforms, etc. Maybe these companies are doing secretly, right? So sometimes they do not publish it, but at least this is something that yet to prove reinforced learning is a major methodology, right? Maybe it's contributing something, but it's not the has not proven to be the major methodology. So these slides I want to convey the message is the class of models. Before you do something control this system, you need a mathematical model of this system, experimenting within this mathematical model or simulation framework. And stochastic processing networks are unified mathematical models to model this real-world system. And many people contribute in the last 30 years, contribute this research. And Mark Harrison certainly is a leading person in that. But Frank Kelly, R.B. Manaba, many people, indeed the people in this community all contribute to build some version of this. So this is just, my message here is that this SPN, stochastic processing networks, are a very broad class of mathematical models. And they perhaps is the right middle layer for us to design algorithms that eventually can be ported into real-world system. So of course you can design algorithms for space system, but it would be nice to have algorithms that work for a broad class of applications. So main message here, the stochastic processing network is perhaps is good set of models to design this efficient algorithm for. All right. So now for challenges in stochastic processing network controls. Often these systems are operating on ongoing basis. Okay, so like hospitals are running 24 hours a day, right? 365 days a year continuously, and so perhaps long-run average cost is appropriate. Okay, so that's the first thing. The second thing is the system has a large state space. Okay, now in our mathematical model, that means an infinite state space. Okay, and unbounded one-step cost. This can be very technical, but this is something if you want to control the total population, the total job size in the system, if the job size is very large, then this to us that cost is very large. Okay. So this unbounded, so this creates technical difficulties for reinforcement learning. The third thing is the time horizon. I mentioned earlier that long-run average cost is appropriate, but this turns out, of course, it's not surprising you see regeneration of cycle is important here. Look at the average cost problem. And so the natural time horizon, indeed, even if it's a long-term long-run average cost, the natural time horizon indeed should be this regeneration cycle. But the system load have interfere with this, right? The heavier load, system heavily loaded, heavier load, the longer the regeneration cycle is. So these are the challenges or the issues that has not been really been focused in the reinforcement learning research. So I'm going to start with the simplest model to illustrate some of the technologies or terminology, okay, terminology mainly. So what's drawn here on this slide is a so-called criss-cross network studied by many authors. And so two circles represent two servers, okay? So there's a S1, S2 are two servers. And these rectangles are buffers for waiting jobs. So there are two type jobs. One is the horizontal one. The job arrival goes through to be served at station 1. After that, moving into station 2. And of course, when moving to station 2, if the server 2 is busy, then it's waiting in buffer 2. After serve at station 2, leave the system. And these vertical jobs arriving into the system and process after being processed at station 1, then depart the system. So here, the real interesting scheduling part, actually decision part, is only for server 1. For server 1, after finishes service completion, after service completion, it needs to decide which job, next job to take from. It should be taken from buffer 1 or buffer 3. That's the decision, right? And for server 2, can be, if we insist server 2 to be, each server to be non-idling, meaning that if there's a job to do, the server should be fully busy. Then for server 2, there really no decision need to be made. So server 1 decision need to be made. And ideally, or often is profitable for the server 1 make decision depending on the state, meaning how many in buffer 1, how many in buffer 3, and how many in buffer 2. So these are the state information. And so a policy prescribe actions in each state. So no matter in each, server 1 observe each state, and a policy should tell server 1 what to do. So one family policy is called a randomized policy, randomized. So I'm just giving you an example of randomized policy. For example, for particular this state here, this time a state have 2 jobs in buffer 1, 1 job in buffer 2, and 3 jobs in buffer 3. Suppose that's one state, okay? So this in three buffers, okay? That's state. And we need to decide action, say, at this point, what server 1 should do, okay? Server 1, okay, so the randomized policy here is the server 1 going to be flip coin to decide what to do. With 30% chance, going to be working on buffer 1 job. With 70% chance, working on buffer 3 job. So is that clear? That randomized policy is that need to flip a coin or generally to through multi-phase die to decide which action to take. Okay, so that's randomized. Of course, it's probability depending on state, right? Depending on state. So if you need to decide for each state, these probabilities, there's the many infinite possibilities. So so this is a very high dimensional problem to describe a policy, right? Because we have infinite states, possible states. So a low dimensional representation of this policy could be determined. What here is a so-called neural network. I'm not going to get into the detail of that. So it's basically give you a function of this these are probabilities depending on state. Give you a function of the state. So each state you have here, and I give you each state input. Each state give you a probability distribution. Okay, so a neural network can do that. That's just one example of representing policy. Now there are benefits of introducing randomized policy. Let me just go ahead to emphasize here is that it allows you to change policy slowly. Okay, so slowly meaning that from 30% to 40% or 35%, right? So that's changing slowly. Versus as the other extreme is a so-called deterministic policy. Deterministic policy, you either serve buffer 1 or 100% serve buffer 1 or serve 100% serve buffer 3. And these policies often will create some issues, okay? So I will talk about that later. So this work has been last few years that Mark and I have been working on. So the contribution is that we first give a theory, some theory, a justification of one family policy called PPO, Proximal Policy Optimization for MDPs. And this is a generalization in the following sense: is long-run average cost. The previously was the focus on discounted cost. The second thing is a countable state space, and previously is for final state space. Okay, And the other thing, the contribution is that we numerically demonstrated that PPO can generate state-of-the-art control policies for multi-class queuing networks. And for those of you familiar with this model, the multi-class queuing networks are special class of stochastic processing networks. And many of us have focused on their control in the last, say, 20, 30 years research. The third thing that we found that the neural network architectures and the hyperparameters can be more or less automatically adjusted. Basically, there's no tremendous effort specific tuning for, if you give me new queuing networks, I don't really need to try hard to start from scratch to design a new class for neural network, etc. So that's the, we found this is going to be useful practically for other people to experiment. The last part is that we did focus on the value function estimator turns out that's, at least in our experiment, that's one of the key factors to our success. So I just mentioned that. So I should mention that this talk is mostly demonstrate a concept numerically to show that that there is a scalable algorithm to find near optimal policies for stochastic processing networks. And we are still shy of experimenting this in a real world operational system, right? We have not gone to that stage. I think that's the I mentioned about earlier Amazon robotics. I think this operations in our community, generally broadly speaking, I think this is the being able to demonstrate that a certain class of algorithm can really make a dramatic impact in real world operations is important to our research, important to our profession. And I want to commend that other groups like Shamano has been really working in the data center setting in the process of demonstrating that reinforcement learning is a viable, important class of algorithm to improve the data center operations. And for that matter, Neil Walton has been working on some traffic control, traffic control problem. And these are, I think, these are very important efforts to complementing the theoretical research that we all love to do. So my first part is to give some theoretical motivation of PPO algorithm. Okay. So Markov decision process. I'm not going to give the detailed description of that. I assume that everybody has some background on that MDP. So I just draw out something that maybe you are not familiar, right? If you are not, not commonly used these formulas, that if you not focus on your research in this area. So assume, say, for the moment, all the state space is finite, and action space is finite. Okay. So if I'm given two policies, in particularly, if I'm given pi 1, and is this, I think there's a, maybe order difference, should be pi 2 minus pi 1, okay? So, so given a current policy pi 1, I want to find a policy that's improving over previous policy, okay? Now this is very common, right? Suppose you are Uber, and you're currently operating some matching policies between drivers and passengers, and this has been going on for 6 months. And maybe you want to find another strategy, another policy matching, right, to see what happens. So that's the setting. So pi 1 is current policy that Uber has been using the past 6 months. And pi 2 is something that maybe new policy will want to experiment with, okay? So the issue is to find this new policy, pi 2, okay? And so the performance difference, the left side of the two policies, performance difference, and I think should be pi eta pi 2 minus pi 1. That's equal to this expression here. So what is this expression? First of all, this is a so-called advantage function of under current policy pi 1. So x is state and a is the action. So it's given by here. That's the under current policy. That's the advantage function. Now, so what's an advantage function? It intuitively very clear here. So you currently at state x, the policy is pi 1. But I intentionally, my first bit, currently, I can intentionally to deviate from current policy pi 1. I'm taking action A. I do not follow pi 1, taking action. What happened to take policy by action A? And afterwards, from next stage on, you follow pi 1. So basically, if this one is a positive, so suppose I'm doing minimization. If this one is a positive, meaning that this action A, the cost is worse than previous policy pi 1. So maybe action A should be avoided. In the meantime, if this one is negative, maybe action A is better than pi 1, previous policy, the current policy you're using. So this advantage function give me a clue which action, how can I improve over current policy. So again, advantage function try to measure if this one negative, meaning that this action A at x is taking action A at x is better than taking pi 1. Okay, follow pi 1. So if it's positive, if I do minimization, okay, if it's positive, then maybe I shouldn't take this action A. Okay, so that's the advancement. Okay, so that's this one here. Pi 2 is yet to the new policy you want to find. Okay, and what is this space value here? It's space value here in terms of x. X is averaging over what? Averaging according to distribution of new policy pi 2. Okay, so you can see this expression is very difficult to evaluate because pi 2 is the new policy yet to find, and you want to evaluate this expression under a new policy which we certainly don't have data to evaluate this expression, right? You can see that. However, once you written down this, I'm going to talk about this. Okay, so what is eta here? Eta is random average cost. We focus on random average cost setting. And v pi 1 is defined to be the value function. Okay, value function under the current policy. So you can see it's basically it's current per state cost. G is per state cost. And centered around the average value. Okay, so that's called a relative value function or simply value function. All right. So from this formula here, you can see the base strategy for pi 2 perhaps is to for pi 2 is to be greedy. If I want to minimize this expression here, I want to take the most negative one, right? I said earlier the action A, if it's this expression is negative, then that's a better action than taking current policy pi 1. So perhaps the new policy is should taking the action that makes this most negative. And indeed, that's the traditional called policy improvement algorithm. I mean, that's the policy iteration algorithm, the MDP, very well known policy iteration. So if you have current policy pi 1, the new policy should be greedy. Just take the whichever action that minimizes this. And turns out one can prove this one is convergent, and this infinite space, finite action space, you can prove it's actually converging finite number of steps, right? You find optimal policy. You continue to iterate this way. So this is a policy improvement algorithm. What's the problem? The problem is in general, this is very advanced function is very difficult to evaluate, impossible to evaluate accurately. Now, in the case that the infinite state space that I'm going to talk about, right? It's certainly you are not able to, right? You are not able to evaluate this exactly. So your advanced function is has error. If you now follow this one to be greedy, then the error will maybe drive you wrong direction, right? What you get greedy policy is not improvement anymore. All right. Indeed, this has been commonly observed in the last 30 years. This is called so-called channeling, something going on. What you thought that you're doing improvement, but it's actually not. The policy, what you get is the actual policy is not improvement, and this is because the error evaluate. It's not possible to evaluate this advanced function exactly. So, so that's that. Now, okay. Let's look at this one here. Furthermore, here, right? So ideally, you want to optimize this one here. You want to find pi2 to minimize this expression. Okay, minimize the expression. As I said, this one, the pi2 is yet to be found. And this one here, its space value here need to be evaluated according to state distribution pi2, which is very difficult. So the one immediate idea is maybe, okay, let us just replace this space value, follow the state distribution of pi1, because pi1 is something that we know much better, right? After all, like for example, that hypothetical example that Uber has been playing with pi1 for the last 6 months, right? We have a lot of data, so we can evaluate this expression using past 6 months data, right? No problem. Okay, so that's exactly what Kirkcaldy-Lanford did. That they just replace this that expression, replace the state distribution according to the current policy. Then it's reduced the maximization or minimization into this finding this pi2 into here. The only thing to searching for is the pi2 is here, finding this one here. That's indeed they did, and but unfortunately, if you minimize this one policy here, this policy doesn't guarantee it's going to be improvement. It's not itself. However, they proved that if you do conservative update, okay, conservative update. So this pi tilde, if you minimize this expression here on this one here, that's maybe it's too drastic changes from previous policy. So that may not give you actual improvement. What they actually now do a conservative update. So you just, with the alpha percentage, you keep the previous policy, you only change to new policy pi tilde with the remaining probability. Then, but when alpha is large enough, close to 1 to 1 enough, then they can prove this pi2 is guaranteed improvement. And this work, this paper really generates this insight that really the starting point for a server class of algorithm, and this is all related to the the name of eventually lead to this PPO. Okay, so this conservative update turns out is maybe too conservative or too restrictive, and this way, and so this new class of algorithm, this relate the many names are associated with that, and the PPO is one of the name. So that's the background here. Okay. So this is to inspire this new family of algorithm. So let me, this is the first result here that I want to spend some time on. So you see here that this expression that the first term, the expression is is replace earlier the distribution pi 2 to pi 1 here, distribution under the new under the old policy here. And this is the first term is the one that the Kirkcaldy and Lanford they optimized over. Okay, so this one here. And what this band here says that the true performance, okay, there's upper band, okay, true performance, there's upper band, okay, by this side. And so we not just look at the first term, but look at also the second term. Second term is to measure the difference between two policies, okay, difference of the pi 2 over the new policy over the current policy, the difference, measure the difference of the current policy. So that's a band. So the importance of this kind of band is to promote the algorithm saying, I'm going to talk more about the algorithm, but let's go ahead because this is important to motivate why to establish this band. If I have this kind of band, then perhaps what I should do is to minimize the first term, make it very negative. Okay, I want to current policy, I want to improve, find a new policy. So the new policy, I'm going to minimize the first term, make it very negative. And why keep the second term to be small? Second term small, meaning pi 2 may be close to enough to pi 1, so that does not destroy the gain, the negativity from first term. Therefore, the new policy pi 2 will be true improvement over the previous over the current policy. So the one thing here is okay. So for you to appreciate, I don't appreciate this one here is that what's in literature or this band here from Schumann 2017 paper and other paper is to band. This band is a factor was established in the discount setting. Okay, discounted MDP setting. And this factor here is the factor 1 over 1 minus gamma. So we know that in theory that discount, average cost problem can be approximated, can be very close to discount factor properly scaled, right? But if you have this factor here, 1 over 1 minus gamma, 1 minus gamma here, when gamma goes to 1, this factor will blow up. So we cannot get this average cost performance band, okay, improvement band, through the results from the discount counterpart. In other words, mathematically, we cannot prove this band through discount counterpart. We have to attack this problem directly. And so we introduce this coefficient here depending on so-called the ergodicity coefficient, okay? So I think the important thing is to remember that this one is a finite number here. It's not blowing up like a gamma, okay? 1 over 1 minus gamma. Gamma is discount factor. So that's the first part. The second part is the infinite state space, okay? Infinite state space, and it's a trickier problem, and that's what we are focusing on. Our experiment, the Q network, we do have infinite state space. So in this case, we need a so-called drift condition, Lyapunov function, okay? So if a Lyapunov function, this is the drift condition. Under this condition, and this theory is very well studied, presented in Ma and Tweedy, their book, and the second version is 2010. And so if you have such a Lyapunov function V on the state space, okay, map to positive number, then this so-called relative value function is actually under the current policy is well defined. So again, the relative value function, okay, this should be P under a particular policy, okay, maybe should be P pi. So this P is under a particular policy. Under a fixed policy, we have a Markov chain. We want this Markov chain to be positively current. Indeed, it's more than positively current. We need this Lyapunov function satisfied. This actually imply the Lyapunov function, the Markov chain is actually something called a geometric ergodic, okay? So we need this condition, drift condition. Under this drift condition, then if this cost function is not too big, if this function is not too cost function not too high, then this value function is well defined in infinite state space. And furthermore, it allows us to establish policy improvement bound. So let me just mention this here. Go over this slides. So that's the current performance, okay, and the current policy, pi 1. So I want this current policy is good enough, okay, good enough in the sense I have Lyapunov function, okay, Lyapunov function. And as long as the new policy pi 2 is not too far away from current policy, not too far away, meaning that two policy, I'm not going to get into the detail of this definition, but the pi 2 is not too far away, okay, from that. Then the second new policies also have state distribution. That's nice, right? The new policies also have state distribution because these are infinite state space. There's no guarantee the new policy will be positively current, okay? So if the new policy not too far away from current policy, it has state distribution. Furthermore, performance has this difference. All right, and it's very similar. The first term plus the second term, okay, second term. So this is suggesting that I can go ahead to optimize the first term while keeping the second term small. Second term small meaning keep the pi 2 not too far away from pi 1. All right, so that's the theory part, okay. So I think that's already said enough here. So this is the previous bands is really allow us to minimize the first term and keep the second term small. Okay, minimize first term, keep it small, and that's the main idea in Schumann's and two papers. Okay, in the discount setting, and we now can do this for the average cost setting as well. So so now let me. So how do you minimize the first term? Okay, first term, and this is the current policy here. Pi I is the current policy in the ith iteration. I need to find a new policy. In order to find new policy, I need to solve this optimization problem and keep the second term small. So it's a constraint optimization problem, right? There are several issues. One is a constraint optimization problem. Second issue is this is expect value. There's expect value going on here in terms of state distribution. So for that, we can use data, right? We can use, suppose we have enough data from current policy, then we can, strong law of large numbers allow us to use a sample to approximate this expect value, okay? So that's what are we going to do? We're going to optimize a sampled version of this one, minimize sampled version of this function. The second part is this is a constraint optimization. Constraint optimization is a nuisance, okay? It's a nuisance, and can we turn into a proxy unconstrained optimization? Use a function, some proximal function, to turn this optimization problem, constraint optimization problem, into non-constrained optimization problem, and that's what's going on here. Is using this a proximal function. Okay, so the first term, this is just like that before, the object value here, and the second term, this clip here is taking care of the constraint. Okay, taking care of the constraint. So I am not going to get into detail of that. This why to take this proximal function. Okay, so essentially, basically, the main idea is to turn this constrained optimization problem into something unconstrained optimization problem. All right. So to deal with this expect value, as I said, we can use a sample. Okay. So under current policy, we generate data. Episode meaning generate data. Let's say for Uber's case, maybe they can keep track of what the last 6 months data, right? Under current policy. So we generate episode under current policy. All right. So take the sampled version of the previous objective value in the first display, the sampled version. So you see here, assumes this advanced function is well estimated. Advanced function is under current policy is estimated. So the only unknown is this pi theta, right? This is the only unknown. So we can, this optimization problem, I call the P here, the PNN, neural network. Okay, so the this optimization problem, this can be solved by standard solver, okay, standard solver. Now, of course, there are issues whether this function is a convex function or non-convex function. Indeed, actually, let me just say that it is not if the pi policy is parameterized by neural network. In general, it's not a convex function. So, so indeed, the shape of this function as function of theta here is not very. It's not very clear. That although there's a lot of interest, try to understand this optimization problem. So let me. With this, we cannot do the iteration, right? So we estimate the value, current policy, estimate current advanced function, presumably using data. I will talk a bit more about that. Then formulate this optimization problem, also using the data, okay? Using the data. And then do the optimization. You find a new theta, theta I plus 1, and then that's pi theta I plus 1, that's your new policy. You do the iteration, okay? So that's the algorithm, PPO algorithm. Now, of course, there are some parameters like epsilon, the clip size need to be adjusted, okay? And there are a few other parameters. How do you solve this optimization problem? The optimization solver, there's some other parameters. I haven't talked about that. And also, how do you parameterize this family policies? I haven't talked about that. I briefly mentioned this toward the end, but let me go ahead to present some numerical results. So what I'm going to do here is this is a so-called re-entrant line. Not quite re-entrant line. This actually is a multi-class queuing network. The two type arrivals. So the one type arrival goes through the entire network 2 times, 2 passes. First pass, the first row. Then they coming back in second pass, goes through the network and out. And there are a total of L stations. And at this point, each station has a single server. Okay, so I have a total of L servers. Okay, so in our experiment, L is going to vary. Okay, vary. Okay, and also for this network, there are another second class arrival. So second type arrival goes through network just once. All right. So you can see that each server, each station, there are 3 buffers. Okay. Each station 3 buffers, and again, the policy is for each server when it's ready to decide which job, which buffer to work on. You either choose for station 1, you either to choose to work on buffer 1, buffer 2, or buffer 3. Right. So these are decisions. And the cost is here is the total number of jobs in system at this time. Okay, that's in immediate cost. And so the ultimate system costs the long run average. The long run average number of jobs in the system. So here is that we compare our PPO performance with other previous policy. And first of all, for different size of network. So this is for L equal to, this is the L equal to 2. Okay, so 2 station, 3 station. The largest one we experimented with 7 station. Okay, 7 servers, and each station has 3 classes, so there are 21 classes, right? And we didn't put a constraint on the how many what's the buffer size for each buffer. And here the load is 95% for each station, okay? And the column, last buffer first served, first come, first serve, etc. These are the known policies, okay? Known policies studied in literature. And the one that we really want to compare with, that's the state of art in literature, is called robust fluid policy. That's being created by Dimitri Persima's group. Okay, so this robust fluid policy, that's the second last column. Okay, so this is the column that we compare with, and then the last one is this PPO algorithm, and so what you can see here is that the PPO algorithm can consistently reach this or succeed, surpass the performance of this robust fluid policy. So let me give you a bit more details about these algorithms. Okay. First of all, as I said, PPO algorithm is this algorithm is a policy improvement algorithm. It's a policy doing policy iteration. So you need to start from something. Okay, start from some policy. What we did is we started for the proportional randomized policy. Okay, and this is fairly for those of you familiar with literature. That's a very similar in continuous time setting that Morey-Bramson have studied head of line proportional processor sharing. That's pretty much equivalent to that in the continuous time setting. So that's the policy we start from. Okay, that's we start from. What we find that if we start from random policy, a random initialization of the neural network, right? Each coefficient of neural network gives us a policy. If we randomly initialize the coefficient of neural network, that's give us pretty much a random policy. And we find out that this random policy is typically unstable. So makes system blow up. Okay, so unstable. And from there, it's very difficult to improve upon. We actually don't know how to improve from an unstable policy. Okay, so the success so far is using domain knowledge, using our prior knowledge, what are good policy to start from. Okay, that's first thing. Second thing is I mentioned earlier that we can automatically adjust the policy neural network and the value function neural network. I haven't talked about the value function neural network. I will mention briefly, hopefully quickly, than that. And I mentioned no additional tuning of that optimization solver. Remember there's an optimization problem there. We pretty much use default. There's one solver that's been very popular in machine learning community, so-called Adam. It's a theoretical study guarantee is not well understood. However, that its empirical success has been tremendous in many machine learning algorithms. And we found that this solver is also effective in our setting and with a little tuning. So basically, we mostly use a default. Okay. And the third thing, that the last point that contribute to our success is that we combined contrivariate methodology proposed by Henderson and Glenn with the known variance reduction techniques. So when you estimate value functions, we use the regeneration estimation. We know that discounting can be helpful to reduce variance. To estimate value functions, and that's well documented in literature. Another thing is multi-step bootstrapping. That's essentially the so-called temporal difference learning TD lambda. Okay, so that's been in literature has been used. What we here combine advocate that we want to use contrivariate. Okay, that was studied by. In Henderson Glenn 2001 paper. I mentioned, I think I will not get into detail of that, but I want to mention what are we talking about here, the value function. So remember that the advanced function is equal to, there's a formula if f is a truly value function of the current policy pi. But the current policy pi value function, we don't know. We don't have access to it. We need to estimate, and so f psi is a current estimation, and we're using a neural network to approximate this value function. Okay, and so once this approximation can be obtained, the advanced function can be computed here, okay? And in particular, I highlight here, the red one here, that I using this space value here, this summation represents space value. This requires that we know the model, right? This requires us to know this transition probability, all right? So how do we estimate this, approximate this value function? Well, what we do is we estimate this value function at select points, then do a regression to find the value function, approximation value function in the entire state space. Remember, our state space is infinite, right? But we can only estimate the value function at a select point, a few finite many points, okay? So that's the idea. Now, all the variance reduction techniques that I talked about a bit earlier, I mean, these three things here, including control variant, is how do you estimate this target value, this value function at a select point. And I think my time is moving fast, so I think I shouldn't get into, I'm not going to get into different estimation here. The paper talk about that, so let me highlight what's going on here. Yes, using this figure. On this plot here, the x-axis, remember the policy iteration steps, or PPO iteration, policy iteration, right? So, for example, initially we start with randomized policy, proportional headline, proportional sharing policy, right? It's gradually improving as do the policy iteration, gradually improving, the cost going down, okay? So what we did is for small size network, we know the optimal policy, right? This optimal policy, the value is about slightly above 15, okay? So here the green curve here. The red one is the performance for robust fluid policy from diminished Bersimas group, red one, okay? Now, the pink one, both pink one and this dark one here, the doing PPO. The difference is how the value function are estimated. So the value function at select point, the pink one is estimated through regeneration. We use a traditional variance reduction technique in literature. We use regenerative method. We use discounting. We use the temporal difference learning. But still, you see, cannot really reach the best performance. The dark one, we introduced the control variant, the methodology used in Henderson and Glenn. And you see that dramatically improved the performance. So I'm not going to talk about that. So let me go ahead to conclude my talk. So what do we have done? I think these networks, as you can see, these are very large. I mean, very large network. Okay, by conventional standard, our standard, maybe not to the truly machine learning community, maybe still not large enough. But the question is, okay, so what we have demonstrated, at least for example, that deep reinforcement learning framework is possibly a framework to overcome this curse of dimensionality, okay? So can generate effective control policies. And indeed, we want to go beyond these Q networks for other stochastic processing networks. This has been, okay, we did one piece of work for ride-hailing service platform for matching passenger and drivers, and we also demonstrated that in that setting we can also beat some previous algorithms. Okay, so that's one application, and we're currently working on the hospital operation problems that's still in progress, and a few open problems. I think this there are several things. Okay, so one thing is how do you guarantee improved policy? I mentioned earlier that my pi2 in the infinite state space case, I start with a policy. Current policy has Lyapunov function, but how do you guarantee that improved policy also have Lyapunov function or also positive current? I mean, it's a having state distribution, no problem. We prove that, but how do you know that it's also geometrically ergodic? And that's something that that we have not been able to resolve that issue. All right, so let me stop here.
Okay, so thank you very much, Jim. I'll clap. Hopefully you can hear everyone clapping virtually in the background. So yeah, thank you very much
Should I
for a
stop
great
sharing?
talk. Why not? Yes, let's do that. And then